Welcome, Chemistry 12-2. This is the first video for week 9. We've made it. We're finally here, our last week, and we're going to continue, kind of finish up our conversation on organic chemistry. So we're moving from chapter 22 into chapter 23, and we're going to talk about hydrocarbon derivatives. And hydrocarbon derivatives are basically hydrocarbons, but some other types of elements are going to be introduced into the hydrocarbons. And before we can actually move on to some new families, we need to discuss what the importance of a functional group is. So the functional group here is actually going to be a combination of atoms that really give the product its chemical and physical properties. We've looked at chain or aliphatic hydrocarbons. We've looked at ring hydrocarbons. We've looked at hydrocarbons with single bonds, double covalent bonds between the carbons, triple covalent bonds between the carbons. We've looked at this funky molecule called benzene and aromatics. Usually the parent chain or the bulk of a hydrocarbon or even an organic compound is inert. And we know that inert, here it is right here, in most chemical reactions involving organic molecules, the saturated hydrocarbon skeleton of the molecule are chemically inert. So the majority of the molecule, usually the long parent chain, the carbon-hydrogen parent chain, is not very reactive. They're very stable bonds. They're not very reactive. They're nonpolar. They're quite strong, and so they tend not to want to break and rearrange. So most organic compounds, most organic chemistry is actually functional group chemistry. So when two compounds react, it's not the entire compound that's rearranging. Sometimes it's just the functional group that's going to be the reactive section. And so a functional group is not the entire molecule, it's going to be just a group of atoms. And we're going to be able to use that functional group in order to classify or to organize our organic compounds into families. We've already looked at some families with hydrocarbons. We looked at alkenes and alkynes. We've looked at alkanes, cyclohydrocarbons, or cyclic. We've looked at aromatics. And we were able to put those chemical compounds into different families by looking for one important thing. We didn't call it a functional group in chapter 22, but that's exactly what it was. So we knew that alkenes had to have at least one double bond. We knew that alkynes had to have at least one one triple bond. And so that actually is a functional group. So if an alkene is going to react, the reacting atoms that are going to be involved are those branches or those carbons that are around that double bond. Or if it's a triple bond, if it's going to react in a chemical reaction, then it's going to be the branches or the carbons around that triple bond that's going to be reactive. So you might have guessed it, we're going to talk about some families in this chapter, some new families, and we're going to talk about how to name them and how to draw them, so that's going to be our nomenclature section. But the extra part in chapter 23 is we're going to take a look at 5 organic chemistry reactions, 5 types of reactions that might happen with organic compounds. There's many, many reactions. We're just going to take a look at the first 5 basic types of reactions that might occur. And those reactions will be cinched around the functional group. So a definition for a functional group is a specific arrangement of atoms in an organic compound that is capable of chemical characteristic reactions. So this group of atoms, it's usually quite small. Sometimes it's at the end of the molecular compound, sometimes it's not. And it's going to be the center of reaction when we do a chemical reaction, but it's also important because it usually provides the chemical and physical properties. So if you have this functional group, you have similar properties to every member, and therefore you're like a family. So if you think about families, we know that families tend to have 1 or 2 specific surnames, and those surnames are kind of how we recognize or organize. So think about being at a family reunion, and in my family you might have some Cummingses, you might have some Howrens, you might have some, um, I'm trying to think of what the other families in my in my group. Anyways, you'll have many surnames, and so we're at a family reunion, but you can organize people into different families within that family reunion. Same thing here. Functional groups are going to help us organize organic compounds into families, and every member in a family will have a similar chemical and physical makeup, and that's because of the functional group, or that small little group of atoms. And therefore, when they do react, it's going to be those small little group of atoms that react with you. Now, sometimes functional groups, up to now, they've just been carbon. They've been double or triple bonds between carbons. Here, we're going to branch out a little bit. So some of our functional groups will have, most of them will have oxygen. Some have nitrogen. You can have sulfur. So we're introducing, not just halogens now, we're introducing a few new atoms to our organic compounds. But you can see there's not a big array. Most organic compounds are made up of carbon, hydrogen, halogens, and one of these four, or a couple of these four. So there's not a big array of atoms involved in organic compounds, and they can get really, really big. But again, it's like the iceberg. The majority of it is inert, not really reactive. It's going to be that little piece above the water, that functional group, that's going to be involved in the chemical reaction and create the chemical and physical properties that we're going to see here today. Okay? So just flash forward. You can see here we have some functional groups. Of course, we're not going to talk about all of these functional groups, but you can see here's an S, here's a couple N's, right? Here's a triple bond, but there's a nitrogen there. We've talked about the red ones. So here's our single bonds, our double bond, and our triple bond. So those families we've talked about. We will talk about a couple of these blue ones. We've kind of talked about this orange one where we have a hydrocarbon chain and an X. So you see the symbol R and you're wondering what the heck is R? I always think about it as the rest of the compound, because we're going to highlight the functional group, and the rest of the inert compound often is recognized as R. And R is really just an undistinguished number of carbons. So it can be a short carbon chain, it can be a long carbon chain, but it's the rest of the molecule, and then we're highlighting the functional group. We'll also take a look at some of these red ones. So we're going to take a look at aldehydes. We're going to take a look at ketones, carboxylic acids, esters, and that's probably about it. If we had more time, we'd talk about amines and amides, but unfortunately, we don't have that time. But I just wanted to give you a kind of an introduction to some of those crazy functional groups we see out there. So these would just be the tip of the iceberg, and they'd have a large, large component of just hydrocarbons underneath the water that would make up the entirety of the molecule. Let's look at the ones we want to talk about a little closer. This table is in your textbook. It's table 23.1, and what it does is it highlights the functional groups. And that's what I'm going to do right here now. And you might say, what? We haven't even talked about any families yet. Correct. I want you to be okay with functional groups and kind of how to recognize them. And then when we get to the families, it's going to be a little faster. So these are the functional groups we will talk about when we talk about hydrocarbon derivatives. So hydrocarbons that have an extra type of atom other than hydrogen and carbon. We've talked about the top one already. We called it alkyl halides, but the easier name is halocarbons. So halo coming from halogens, group 17. So halocarbon is going to be a molecular or a hydrocarbon that has a group element from group 17. The general formula, now when we talked about general formulas with hydrocarbons, we looked at CnH2n plus 2, CnH2n. So we were just looking or counting how many carbons and how many hydrogens. Now we've got extra atoms. So our general formula might look a little different than it did before. So here we have that R, so the rest of the molecule plus X, and X is going to be this halogen, right? So it could be an F, a Br, a Cl, or an I. And so if we had like chloropropane, the rest would be propane, and the chloro on the first carbon would be the X, okay? And we just call this a halogen functional group. So functional groups, you can recognize them by what they look like, but they also have a name that go along with them. One of the families we're going to talk about are alcohol family, and the alcohol family has a functional group of OH. So again, you can have a chain of carbon, so the rest of the molecule, but then you have this OH, and you might have more than one. Right up here, remember, we could have more than one halogen attached to a molecule, or we might have more than one OH attached to our rest of the compound. The OH, when we find it, its name is hydroxyl. Hydroxyl is the OH group, and we'll see it again. Down here is an ether, and in ether, it really is taking a big hydrocarbon and a big hydrocarbon, or even a small hydrocarbon and a small hydrocarbon, and joining them with this oxygen molecule, oxygen atom in the middle. So ROR, it's known as the ether group, and that, we'll take a look at that family. These guys are kind of like first cousins because they share the same functional group. It's not the functional group that makes them different, it's where the functional group is in the molecule. So here you can see the general formulas look quite similar. The only difference is down here there's two R's. So here's a chain of hydrocarbons, a chain of hydrocarbons, like a little iceberg, and here's the functional group that we are really focusing on. Down here there's just one iceberg, and this here is the functional group. And you might recognize this because look, it's a C, right? And it's an O, and it's a double bond here. So when you see that C with a double bond to the O, it's known as a carbonyl group, right? Both of these have the same functional group. It's not what functional group they have, it's where the functional group is. Here with aldehydes, there's no R here, which means this is the last carbon or the first carbon, whichever way you want to look at it. We think of it as the first carbon. This is the first carbon that has a double bond to the O. And down here, there's two R's, which means the double bond to the O is on one of the inside carbons or one of the middle carbons. So it's where that OH is. But, sorry, it's where that double bond O is. But they're known as carbonyl. I could talk about functional groups forever, so I'm just going to rush down. And the last two we'll talk about. These two down here we're not going to have time to do. So the A's, the amines and the mides, they're interesting because they have a nitrogen. It's the first time we see a nitrogen. But unfortunately, we don't have time to talk about them. But we will talk about carboxylic acids and esters. And again, they're kind of like first cousins because they're very similar with their functional group. We call this an ester group. We call this a carboxyl. Now, where the heck did carboxyl go? Well, we've got hydroxyl, which is OH, up here with your alcohol. So we have an OH here, hydroxyl, and we have a double bond to an O. So we have both of them here. We have a hydroxyl and we have a carbonyl. And when they occur together like that, it's actually called a carboxyl. So we sandwich them together. So carboxyl is when you have a double bond to an O and a single bond to an OH on your terminal carbon. This might look familiar to you because we often see it written as COOH. Remember those acids, organic acids we talked about? We kept saying we'll talk about those later, we'll talk about those later. Well, here's the COO, here's the COOH. Here are the vinegar is a carboxylic acid, oxalic acid, right? So any acid that ends in COOH, it falls into this family. That's its functional group. Down here, we are going to replace that H with an R, and we'll talk about how esters are created. So those are some functional groups. So just to finish this up quickly, so I can move on to something else, you can see here I've just put a few molecules down, and we're going to circle our functional groups and name our functional groups, okay? So think about it, and if you have to memorize anything, it's really just like we had to memorize the prefixes in the last chapter. It might be good to recognize and memorize these functional groups, and we're not using a lot of them, so, you know, I don't think that's asking too much. It will definitely increase your okay, I'm just going to pause for a second because my airliner's not working. Hi, I'm back without an airliner, but that's okay. So we're going to take a look at these molecules, and we're going to circle the functional group and name the functional group. And we won't do all of them, but we'll do a few, and you can come back and take a look at them. So here we have our first molecule, and I always tend to kind of look at the last carbon. That's usually where they draw the functional group. Not always, but usually. So I'm going to circle this right here, and I might have to make it a little bigger, but you can see that this would be the R part, the rest of the molecule. Here we have, now be careful, This is a double bond to an O. It's to the side instead of up. It could also be below, so just be careful. So it is a double bond to the O. It is a carbonyl, okay, so it's a carbonyl group, and it's actually an aldehyde, but we won't get into what family yet. We'll keep that for a little later, okay? And so let's move this guy up here. And if we go over here, we're looking around, and you're right, we see an OH. And there's that OH. It's a hydroxyl, okay? A hydroxyl group. This is an alcohol. So we know it's alcohol because of the functional group it has. We know this is going to be an aldehyde. It's the double bond to the O is on the last carbon, so it's an aldehyde, or the first carbon, your perspective. Oh, yes, of course, that's what's going to happen. So if we take another one of these and bring it down, if we look close, and again, sometimes I suggest looking at the bottom, and you can see, make this circle a little bigger, we are circling our functional group. There's an O, but look closer, right? There's an OH and an O. We have the combo here. We've got a carbonyl, we've got a hydroxyl, and together they make a carboxyl, right? So that's the hybrid of the two, carboxyl, okay? So this is a carboxylic acid. Over here we search and search and search and search and search, and you'll be surprised to see that it's really just this single bond, okay? So this is an alkane. Okay, so an alkane in this family here. Over here we search and search and search, and we look for these funky ones. We might not find the funky ones. We might find our double bond there, right? So this is an alkene. So we've looked at some families already. We didn't really call them functional groups, but we looked at them. If we move down here, oh, this is going to drive me crazy. If we look down here, we see, again, I always kind of check the last one out first. Oh yeah, it's not actually really that hydrogen there. That's just mine. It's this one right here. Okay, I think we're getting a little overzealous with this one here because it's really just the C and the O there. So this is a carbonyl. Okay, a carbonyl. And we could do this all day. I'm not going to take the time, but we could do this all day. And there's a few more there to practice. And there's a few in your textbook to practice as well. I will show you this one. Here's a triple. Here is your carbonyl. A carboxyl. There's two together. Here's a carbonyl. This is a ketone because it's not on the last or the first carbon. It's on one of the middle carbons. This one is, sometimes you see it in this array. You have your double bond. So I'll just clone that. You have your double bond to the O right here. So it could be high, could be to the right, could be below, could be off here at an angle to the Vesper. And this is a carboxyl as well. Okay, so that's what you want to train yourself at, because they're all going to be mixed together on the assignment, all these families. So you have to recognize which family it belongs to first before you can start to name it, and use your functional group in order to help you to find that. Okay. Just before I finish off with two short things, I have put this sheet, so this resource is in week 8 and in week 9. It's called a summary sheet, and what it's done is it's taken all the hydrocarbon families, and so I've used the front side as a model, and the back side I've left blank for you to fill in as you go through these videos, and I think it's going to be a really important resource for you as you do it. So what I have done as a model, I have looked at all of the hydrocarbon families we talked about, including aromatics. I put in my halocarbons here. Technically, they are a derivative, but we talked about them already. And what I did is I put the general formula for each of them. This one, technically, you could also use Rx for a general formula here. Then I looked at the functional group. So what was the part of the group that was the most reactive part? Here it's the halogen, here it's the double bond, here it's the single bond, here it's the ring. And then very quickly in point form, I talked about what the rules were for naming each of these families. And so here was quite a bit because it was where we introduced all of our rules. And then we just talked a little bit about what's the one change, or how do the rules change when you move into a new family. So it took me a bit of time, but it's very, very helpful, and I gave it to you so you can take this on to secondary and you've got a really quick one sheet reference that you can find out how to name all of these hydrocarbons. What I have left for you is a blank backside, and I've listed the families we're going to talk about in this chapter. So I would really, really strongly suggest that as we go through these families, you print this off and you, or do it digitally, put in all of the different functional groups and a quick point form how to name each of the families. So what things do you have to remember? The general rules will always be the same, but what's the one new thing you have to remember in each family? Okay, I did put amines and amides on the bottom. You may leave those out because we're not going to talk about those. But 1, 2, 3, 4, 5, 6 new families we're going to talk about and how to name them and how to draw them. Okay, here's mine completed. All right, we are going to just mention this here because we've talked about these guys already. They are halogen substituents or substituents. It's technically substituents. The halocarbons are your, when a hydrogen is replaced by a element from group 17, it can be fluorine, so they're called branches, and this is fluoro, chloro, bromo, and iodo. We've talked about those, so I'm not going to take your time today to talk about those, but you can see some examples here. Here we have methane, and one of the H's have been replaced by Cl, so it's chloromethane. Here we have 2 carbons with a double bond, so it's ethene, and we have a chlorine on the front, so chloroethene. Here we have a butene, a benzene. I should have had a circle in here. And so this benzene has a carbon. And remember, it doesn't matter which vertice that chlorine is at, because it'll be your number 1. So here it's chlorobenzene with the circle in there. Just one interesting point about halocarbons. The more halogenating happens, so what's this mean? The more halogenated. Halogenated means adding halogens. So the more halogen atoms you have, the stronger the intermolecular attractions, and therefore the higher the bonds. So, the higher the boiling point. So boiling points are all about how easy you can rip apart a molecule. That's what has to happen when things boil. Those intermolecular bonds have to break so that the molecules can leave the liquid state and go into the gas state. So remember, intermolecular bonds, not the bonds within the carbon and the hydrogen, but the bonds between the molecules. And when those intermolecular bonds are really, really strong, the boiling point, you have to have a heck of a lot of energy or a lot of temperature to tear those apart. So the more group 17 elements you have, the stronger the intermolecular bonds, and therefore the higher the boiling point. So halogens or halocarbons can have high boiling points. And I've put some here for you to practice, so you can come back and practice those, but you've been working with those already. The last thing I want to talk about here is our first reaction. I said we were going to do 5 reactions, and we are. Here is a summary table that we'll come back and keep looking at. So we'll fill in the top row today with substitution. So substitution, that's where the word substituents come from. Substitution here, we're going to take a look at what are the reactants. Just like in grade 11, if you had to predict products, you had to find out what kind of a reaction you had. So what are your reactants? Each of these will have different types of reactants, so that's how we'll identify them. What are the products? What are you going to make? And a few examples of each. Okay, so we talked about 5 reactions in grade 11. Double replacement, single replacement, combustion, just decomposition and synthesis. Here we're going to talk about 5 organic reactions, okay? Organic compound reactions. So we're going to take a look at our first one. So it's just like you think. It's just like you see the word substitution and you're like, well, what does substitution mean? Well, I always think of sports teams because I've spent a lot of time on sports teams. And if you're sitting on the bench, you are very interested in substitution because that's what we call it when we stop the game and we take one player off of the floor and put one player back on. It's a complete exchange. And so in basketball, we have to stop the whistle, stop the game, and we stop the clock, and we um, take one player off and put one player on. If we want to put three players on, we have to take three players off. You can only have 5 players on the court. For field hockey, we have 11 on the field. It's a little less um, disruptive, meaning that if you go to the um, center and it's the referee that will, um, you know, blow the whistle and tell you to come in, and you can sub on the fly. But again, if you put 3 new players in, you have to take 3 old players out. And that's the key to substitution. It's a true exchange. So this is what's going to happen here. These are substitution reactions. And so since relatively strong covalent bonds exist within the organic compounds, organic reactions are usually slow. They are not going to happen as fast. And sometimes they need some help. And we've looked at that before. So when we looked at reaction mechanisms and rates of reaction, we talked about catalysts. And catalyst is a chemical that you can put in. It's not involved in the reaction, but it lowers the activation energy so that our reactants can have more successful collisions. So often these organic compounds, you'll see something written on the arrow. That's the catalyst that's going to be used for them. Okay? So a substitution reaction involves atoms being replaced with other atoms. So you're subbing out one atom and putting a new atom in, such as a halogen. So we might put a halogen in and it replaces a hydrogen. So we take a hydrogen off the floor, we put a halogen in. But we can also put in other combinations of atoms. This is another word for it when we put a new halogen in, and we've seen this word before, halogenation. Halogenation is putting a halogen in. Hydrogenation is putting a hydrogen in. Hydrogenation is, okay, we'll get to it, so we won't worry about it now. But halogenation, putting an extra halogen in. And it creates a halocarbon. So we're generating a halocarbon by putting that halogen in. So I'm just going to show you a few examples here, and we'll do one together, and then we'll call it quits for our first video. So here we have, you know, an iceberg, and we're just looking at one H on our iceberg. So we're highlighting one H. There's several of them there. And here's our rest of the molecule. The key with substitution, and this is going to be so, so important, with substitution, you need to have a saturated hydrocarbon. Now, we've talked about that in the last chapter. Saturated hydrocarbon means that you have single covalent bonds. That's really, really important. It won't work. A substitution won't work if you have multiple bonds. So you need to have a single covalent bonds. You need to have a saturated solution. So alkanes, alkenes, alkynes, they're off the table. It's just alkanes, your single covalent bond. And benzene, and we'll talk about benzene. So here we have alkane. It could be hexane, so there might be 6 carbons. It could be decane, there might be 10 carbons there. Here is our halogen, so we're just going to use an X. It could be a fluorine, a chlorine, a bromine. And what happens is we substitute. So the H comes off the floor, and one of the halogens go back in. See, these all halogens are diatomic, so when they're by themselves, they have a little 2. But you can see here the H and one of the X's substituted. Okay, we've made a halocarbon. Here is actually with a alkane. So here's methane, our simplest alkane. So we have carbon, and we have chlorine. See, double. So we're going to take one of those H's off, and we're going to put chlorine on. So we're substituting chlorine. We make hydrochloric acid, nice possible way of making hydrochloric acid. We have chlorine, so chloromethane. Here there was only one carbon, so only one chlorine would join. If you had more than one carbon, you might have more than one chlorine being substituted in, just like basketball. You might put one person on the floor at a time. You might put 3 new people on the floor at a time. So we'll talk a little more about that. I wanted to highlight benzene. And benzene is important because it's unique, right? It's got these double bonds, but they're not really double bonds. They're not really single bonds. They're kind of in between bonds, and they're moving all the time, so we can't pinpoint where they are. So benzene, at each of its, so it's C6H6 is its general formula, because each of its vertices, there's one H, because sometimes there might be a double bond there, and sometimes there might be a single bond there. So they just hedge their bets. They put one H in each of those corners. It acts as a saturated compound. So it acts like an alkane. Benzene, when it reacts, benzene acts like an alkane. So it acts like a saturated solution. So it can be involved in substitution. It's one of these H's out here that are going to be substituted. So we have bromine, it's diatomic. When we substitute, we put one bromine in and we take one H out. So we literally substituted those two molecules, okay? This bromine could go anywhere because remember where we put the branch is our number one. We talked about catalysts. Here's a catalyst. Iron compounds are usually very good catalysts when we talk about these aromatic substitution reactions. Here we have, this is interesting, instead of just starting with an alkane, what if you start with a halocarbon? So you have a chain of carbons with an X. This is actually a really good way of producing alcohols. So when we do substitutions, we can produce halocarbons, but we can also produce alcohols. When we produce alcohols, what we do is we start with a halocarbon, and this little halogen and this OH. Now remember, OH could not come to the beaker by itself. OH is an ion, so it probably brought a buddy with it when it came. So it loses its buddy, and it substitutes in for your halogen, and your halogen substitutes out. Okay, so here is our, the OH joins, and the halogen comes out. Halogens are readily displaced by hydroxide ions to produce alcohols and salts. Fluorine is really not too reactive, right? It's not easily replaced. So if you were going to use a halocarbon to make an alcohol, don't use a fluorine halocarbon. You'd use chlorine or bromine. Here's a couple examples. I know I'm going over my time, so I'll hurry up. So we have here, we've got our, oh, come on, just participate. Okay. So we have methane with an I, so iodomethane. This is our halogen. Here, see how I said OH comes in with a buddy? So KOH came into the beaker. They're going to split up as soon as we get into the beaker, but they came to the party together. The OH is substituted for the I, so now our methane has an OH on it, and it's actually methanol, and we'll talk about how to name in this alcohol. See, there's that functional group. And the K picks up the I that gets kicked out. Okay, so it's really switching partners, but we're creating alcohols because we're putting an OH onto our group. So when you do substitutions, you can create halocarbons, or you can start with a halocarbon and an OH, and if we substitute the OH, a hydroxide, then we can make an alcohol. Okay, so let's put that into practice and just show you quickly. Here we have, you can find these at the end of section 23.1. I was just going to highlight number 6, but if you want a little bit of practice looking for functional groups or naming, you can. Write the names of all possible dichloropropane and that could form from the chlorination, which means adding chlorine to propane. So if we take a look at this, we'll just go down here. If we have chlorine, and it's going to take a little longer just because I don't have my, I'm just going to stop here for a minute, guys, just so I can set it up so it'll take a faster, it will be faster to look at this example. I'm back. So we're taking a look at number 6. It says, write the names of all possible dichloropropane that could form from the chlorination of propane. So just quickly, I set a few things up here. So here's our propane, and we have our H's around it. There's an H out here as well. Here's our chlorine. It's diatomic. So they've told me we're going to make dichloro compounds. So both of these guys are going to substitute in, which means 2 of these H's have to substitute out, right? 1 for 1, 1 for 1. And so there are a few different combinations that can happen. So if we take this guy over here, and we'll just take him, and we substitute out this person, and we substitute out this person, or H I should say, then you can see that the chlorine's going to come in and it's going to fill those places. So it's a true substitution, okay? And so one of the products will be H2, but the other product here you'll see will be 1,2-dichloropentane. But you can see there's lots of different places or different H's we can take out. So it's kind of like isomers. We can come up with a few different examples or different molecules where you have 2 chlorine. Another possibility, so we'll just take those H's quickly back so you can see. We start with this. And what if we substituted the first carbon and the third carbon, right? Will that give me a different combination or a different name? We're really going for a different name. And in fact, it does, because what you get is a chlorine on the last one and chlorine on the first one. So here it's 1,2-dichloropropane. Here would be 1,3-dichloropropane. So as long as you're getting a different name, you've got a different compound there, okay, with some different properties. We could get 2 more combinations, and you've probably figured them out already, but I just wanted to show you this process of substitution. So we could substitute this hydrogen, oops, not that. We could substitute this hydrogen, and we could substitute this hydrogen. So there's different combinations you could come up with. That would give me a chlorine or a dichloro molecule that looks like this and like this, okay? And we have, again, our product would be HH or H2. There's one more combination, and that is if we take this and we substitute out our first 2 hydrogens, so the hydrogens on the first 2 carbons. So if we take that off, and we take that off, and we fill them with chlorines, we get 1,1-dichloropropane. Okay, so I want to do that one with you just to see how the substitution works. So we actually make, and you should draw all 4 combos that would be possible in this case. I'd have to let you know that it was a dichloro substitution, that 2 were substituting, not just 1. If 1 was substituting, there'd only be 1 possible outcome, because putting the, actually there'd be 2 possible outcomes. We could put the chlorine here, so we'd have 2-chloropropane, or we could put it on the front or the back and we'd have 1-chloropropane. So you'd have 2 possibilities if we were just substituting 1 chlorine. I hope that helps out. I know I've gone a little too long, but I will show you. Here we talked about being a saturated hydrocarbon. Benzene also works here. You need single bonds. You can make halocarbons, or you can make alcohols depending on what you're substituting. And here's 2 examples. So we'll continue to come back to this chart and fill it in as we go. Thanks for your attention. I'll see you soon.